It's a great pleasure to be here. I normally talk to neurobiologists, so you're probably the most technically and mathematically informed audience I've ever spoken to. So I'm a little bit intimidated by that. I suspect that I'm going to learn much more from you than you will from me. So I'm going to give my normal neurobiology talk, but I've nuanced it with a few slides and material that I hope will speak to the opportunities for information geometry to be placed into this treatment of Bayesian mechanics, a physics for sentient systems that underpins much of our theoretical neurobiology and formulations of how the brain works and generalizing that to living systems. In virtue of the fact that I put some extra slides in, I have committed the sin of putting too much material into this presentation, and I usually talk too much. So I apologize in advance. We probably won't get to the end of this, but it doesn't matter. All the interesting stuff is at the beginning. So when I get towards the end, if we're running out of time, I'll just rush through the last few slides. So let me just overview what I want to share with you. I'm going to tell two stories. The first is from the point of view of a physicist or somebody who's interested in physics, trying to understand neurobiology, talking about the statistics of life, with a special emphasis on the notion of a Markov blanket. And I'm going to illustrate that intuitively and through numerical analyses. I'm then going to repeat the story as if I was a neuroscientist and basically tell the same story, say the same things, but using rhetoric and using ideas from psychology and neuroscience. And we're going to talk about predictive coding, neural networks. And then right at the end, I'll rush through some toy examples using simulations just to unpack the interpretation of the mechanics that ensue. So I'm going to start off with a question posed by Schrödinger. How can the events in space and time which take place within the spatial boundary of a living organism be accounted for by physics and chemistry? Now, I'm not going to answer that question, but what I want to do is just highlight this notion of a spatial boundary. And Schrödinger was the first person to acknowledge that that boundary in itself was a statistical object. And I'm going to consider that as being fundamental in an existential sense for everything that we're going to be talking about, in the following sense, that if you want to talk about a system, a thing, a particle, you have to be able to disambiguate the states of that particle from the states of everything else. And that separation or disambiguation rests upon, I'm going to suggest, the notion of a Markov blanket. So, can I just ask, are people here familiar with the notion of a Markov blanket? Could you put your hand up if you know what a Markov blanket is? Good. You, sir, can you explain to your friends what a Markov blanket is?
In a Bayesian network, so the nodes represent random variables, and the arrows are conditional dependencies of causation, and the Markov blanket of the random variable are going to be the parents, the children, and the parents of the children.
Perfect. Word perfect. So just to quickly reiterate for those people who couldn't hear, let's take some internal states denoted by the nodes of this graph. And the Markov blanket are the parents, the children, and the parents of the children. So intuitively, the Markov blanket provides a statistical separation in the sense that if I wanted to know my states conditioned upon the rest of the universe, it would be sufficient just to know the Markov blanket states. So technically, if I condition on these Markov blanket states, the internal states now become conditionally independent of the external states, and it is that I'm using as this mathematical image of being able to disambiguate internal states of the system from the external states in virtue of them being separated by the Markov blanket. I'm going to make a further partition here. I'm going to partition the Markov blanket states into sensory states that are not influenced by internal states and active states that are not influenced by external states. And I'm going to, well, first of all, let me just clarify some terminology. The blanket states and their internal states I'm going to refer to as the states of particles. So this will now constitute the particle. And the blanket states of the particle are going to be composed of the sensory states and the active states. So to motivate that, let's just think about systems that I study, like the brain. So the idea here is that the brain can be looked at as constituted by a whole series, a very large number of internal states, all the neural activities, the connection strengths, everything that I would need to list in order to define the state of the brain at any one point in time. And those conditional dependencies here have been written out such that the active states can be considered my actuators, the action that I take with my muscles, that influence external states here, that in turn couple back to my sensory epithelia, my sensory states, my sensory receptors, that cause changes in the internal states that then subsequently cause changes in the active states, and thereby completing this cycle of action and perception, so that I'm coupled, my internal states are coupled to the external states, but only vicariously through the sensory and active states that constitute my Markov blanket. And exactly the same conditional dependency structure exists for a cell. We can regard all the intracellular states here of a cell. We can causing changes in, say, the actin filaments that underlie the surface states of the cell and cause it to move around, pushing the surface states into the external states, external milieu, and they impinge back upon the sensory states that cause changes in intracellular signaling. So in both instances, we have this fundamental structure that we're now cartooning or characterizing as a Markov blanket. Now I'm going to ask you just for the moment to forget about the Markov blanket. We're just going to quickly rehearse the basics of random dynamical systems and then put the Markov blanket back in play to see what it entails. So just thinking in a very sort of general sense about a little universe comprising states here with this Langevin form for dynamics with flow as a function of the state plus some random fluctuations, cartooned here in terms of a trajectory of states over time. And my focus is going to be on systems that possess an attracting set, technically a pullback attractor here, that we can imagine is basically the manifold containing these states as, say, for example, I wake up in the morning, I have my coffee, I do my emails, I have lunch, and I keep on cycling over the manifolds of this attracting set here as I go through my daily routine. This could be at a different time scale, it could be my heartbeat, or it could be the annual trajectories through Christmas and Easter and the summer holidays. Whatever time scale or whatever you want to associate with these states, the key point being that if we consider systems that have an attracting set, have a pullback attractor, then they must keep revisiting the same sorts of states or neighborhoods of the states after a suitable period of time. And under the assumption of the existence of the pullback attractor, I can associate the probability of finding me in any particular state at any particular time with the density of states, and I'm going to refer to that as a non-equilibrium steady state density here, denoted by P. If I can assume that the universe can be written down in this form, and that this particular universe has a pullback attractor, then I can describe the density dynamics as the solution to the Fokker-Planck equation, written here in terms of the density dynamics and the amplitude of these random fluctuations here, and the flow according to this Langevin equation here. Of course, given that this system has attained non-equilibrium steady state, the rate of change of the probability is going to be 0. And that's important for me, because that means I can write out this solution in a way that describes or specifies the flow as a function of the amplitude of the random fluctuations gamma and a solenoidal bit here, and the gradients of the log of this non-equilibrium steady state density. So that's going to be the sort of key result that I've used the Helmholtz decomposition here. Just to make that a bit more intuitive, you probably don't need this, but many people that I often speak to do need a bit more intuition behind this. Imagine that I placed a drop of ink in a cup of water, and normally all those random fluctuations would disperse the molecules of ink, and there would be no attracting set in plane. That's not the sort of system that I'm talking about here. I'm talking about systems that have this almost lifelike self-assembling, self-organizing capacity, where they seem to gather themselves up again. So it's as if I drop the, put the piece of ink in the water, and all the molecules appeared to flow up concentration gradients. And that's precisely what that solution to the Fokker-Planck equation entails. So here I've just written out the Fokker-Planck equation, the solution to the Fokker-Planck equation here with these two components, denoted by gamma and q here, applied to the gradients of the log non-equilibrium steady state density. And those two components reflect this hill climbing, this sort of anti-diffusion behavior, a gradient flow up the concentration gradients, as it were. And the Q is a solenoidal or a divergence-free component that describes flow that circulates on the probability isocontours. So that's basically the setup. That setup, as I'm sure most of you know, underwrites nearly all of physics that we certainly learnt at school and possibly university. I've written some limiting cases down here. If I reduce the amplitude of the random fluctuations to 0, I get conservative systems, and that solution can be rewritten in terms of classical mechanics, Newtonian or Lagrangian mechanics. I can ignore the solenoidal bit and just focus in on the random fluctuations, and from that one can derive all the integrated fluctuation theorems, and the homologs in terms of the laws of thermodynamics from statistical mechanics, or more strictly stochastic mechanics. I can even just interpret that probability in terms of its complex roots, and that Fokker-Planck equation then becomes the Schrödinger wave equation, and from that you can derive all of quantum electrodynamics. But what I want to do is suggest that there's another sort of mechanics in there that inherits from the existence of the Markov blanket. So it shares exactly the same fundaments as classical quantum and stochastic mechanics, but it is special in the sense that it has this Markov blanket in play. And I've just written that down to make two key points about the mechanics that come from having a Markov blanket. So the first point is, because we've got this separation of blanket state of a particle states into internal states mu and the active states A of the blanket, of the Markov blanket, it means that I can actually write down the flow of my internal states and my active states as a gradient flow on exactly the same quantity. So internal and active, namely autonomous states that are not dependent upon external states, share the same gradient flow on the same functional. And that functional is, as we'll see later, a variational free energy functional that crucially does not depend on the external states because of the structure of the Markov blanket. So just to rehearse what we've said so far, if there is a Markov, if a system has attained non-equilibrium steady state in virtue of possessing a pullback attractor, and being a system it is separable from not system and therefore must possess a Markov blanket, then these two things have to be true. That the autonomous states that define that particle behave as if they're trying to optimize performing a gradient flow on the same quantity, and that quantity does not depend upon the external state. So effectively I can work out how I should behave both internally and in terms of acting upon the world in a way that does not explicitly depend upon my internal states. So just to unpack that from another perspective, I've just written out these gradient flows or solutions to the Fokker-Planck equation for the internal states mu and the active states here, and I'm going to liken those to perception and action in a heuristic sense. On that view, then it will appear as if all my internal states, my perception, if you like, my rearrangement of my internal brain states, and the way I behave, the way I go and sample or move to sample sensory states, will look as if they're optimizing the log of the probability of the blanket states given a particular Markov blanket, say me. And that's what I've highlighted here with these cyan ellipses. So how might one interpret that? Well, if you're a psychologist, then you'd interpret that as if systems were trying to maximize their value. And you see this in things like reinforcement learning, optimal control theory in terms of cost functions or utility functions, and expected utility theory in economics. That's nice because the negative of that particular way of quantifying value is just the self-information or surprisal. I've denoted with I of the blanket states B here. That's going to be the thing that's upper bounded by this variational free energy, and we'll see that in a couple of slides. So what that means is that we're trying to minimize our surprise or our self-information, and from that one can spin out principles of maximum mutual information or minimum redundancy, and indeed the free energy principle, Infomax principle of Ralph Linsker, all quite powerful principles that describe the organization of how brains at least couple to the outside world. If we now take the time integral or the time expectation of that surprisal, that's just entropy. So all we're saying is that there is a common drive to the behavior of systems that have pullback attractors and possess a Markov blanket, that they will appear to place an upper bound or minimize their entropy. So that's the holy grail of things like self-organization in synergetics. If you're a physiologist, it's just homeostasis. It's just saying that systems that self-organize and self-assemble try to keep their physiological parameters within certain bounds and put bounds upon the dispersion of those physiological states. So I repeat, it's sort of generalized homeostasis. There's one final interpretation that I want to exploit, and that's the interpretation that perception and action is going to just simply maximize the probability of my blanket states given me. And if I interpret me as a model of my external states, then that becomes Bayesian model evidence, or the marginal likelihood, or sometimes known as the integrated likelihood. So what that means is that I've just written down something which people who subscribe to the Bayesian brain would immediately recognize, that everything we do and everything we think is in the service of accumulating evidence for our own models of the world. Some people call this in philosophy self-evidencing. And that is very closely related to something that's very popular in cognitive neuroscience at the moment called predictive processing, as exemplified by predictive coding. So that's the particular interpretation of this Bayesian mechanics that inherits from the Markov blanket I want to pursue. Before I do that, very, very quickly, I just want to give you a numerical analysis or illustration of the role of the Markov blanket in this sort of predictive processing, or looks as if it is inferring or gathering evidence of what's going on out there beyond the Markov blanket. So what I've done here is simulate 128 little macromolecules. I've equipped them with weak electrochemical forces and strong repulsion of a Newtonian sort. And I've just let them bubble away in a potential well, if you like, simulating an elemental primordial soup. And the reason that I've done this is because I've written down the equations of motion. I now know the conditional dependencies, which means that I can go in there, identify some internal states, and thereby evaluate or identify the Markov blanket states and see if there's a little living particle at the heart of this soup. And if there is, I can start to perform experiments on it in the same way that we perform experiments on brains. So here is exactly the same simulation, but I've now color-coded the internal states in blue. They're surrounded, and typically this is the case of these sort of universes with short-range interactions. The active states are surrounding the internal states, and the active states are supporting the sensory states that are exposed to the environment. And that arrangement underwrites or ensures these conditional dependencies that are required for the existence of the Markov blanket. And what we see here is a little virus-like particle or with a little tail or cilium wiggling away, living happily in non-equilibrium steady state in the middle of this soup. So now I can ask, do the internal states appear to infer, maximize the evidence for an implicit model of the external states? In other words, do they self-evidence? And why would they do that? Well, and this is the bit that I put in for you to see if it makes any sense from the point of view of information geometry. If there's a Markov blanket there, and this system has attained non-equilibrium steady state, then for every point on the Markov blanket, there must be a most likely internal state. And at the same time, there must be a posterior distribution over the external states, which means now that there is a mapping between the most likely internal state and a posterior probability, a conditional probability over external states. So there's a form of synchronization or mapping mediated by a conditional manifold or a conditional synchronization, just because we have attained an equilibrium steady state and there is a Markov blanket there putting that separation in. I won't go through this graphic, it's just meant to illustrate that point, that there is a mapping between the most likely internal state shown as the peak of that blue curve at the bottom here, and a posterior distribution over the external states here. The key point that I wanted to make here is that if that is true, then we can associate the internal states with the parameterization of a conditional density over external states. And that's the big move here. A move which means that the internal states now acquire two sorts of information geometries. They have an information geometry of the sort that would be used to in stochastic thermodynamics. We can talk about the probability distribution of or over the internal states and parameterize that in terms of thermodynamic variables, and from that we can get to the laws of thermodynamics. But there's another information geometry here in virtue of the Markov blanket, where the internal states now parameterize a posterior or conditional distribution over external states. So heuristically, one can interpret that as the internal states holding probabilistic beliefs about the external states, which means that the most likely internal states now become a statistical manifold where the probabilities associated with positions on that statistical manifold are beliefs about the external states. And it's that special, if you like, dual aspect information geometry that I wanted to bring to the table and put to you as an important opportunity to use information geometry to actually understand this more representational interpretation of the flows and dynamics of internal states, provided that there is a Markov blanket. So this is an illustration of one. This is our same suit before. What I've done here is numerically identify that synchronization manifold. And in so doing, what I can do is I can identify a pattern of internal states that best parameterizes the flow of external states. In other words, I can look at the actual state of the world outside in terms of the flow of external molecules, patterns of flow, and I can look at what the internal states think is going on the outside just by reading off the internal states and using this mapping between the most likely internal states and the posterior beliefs about the external states. And that's illustrated here with the cyan lines, the blue lines and the shaded areas in the middle panel representing the 90% posterior credible intervals and expectations about the state of the external states, and the cyan line being the actual external state, basically a mode of flow in the external molecules. And you can see that the true values do indeed lie within the 90% confidence or credible intervals of what is being represented by the internal states. And indeed, if I now just gather together excursions of those external states and look at the and superimpose and take the average of the internal states, we see something on the bottom that looks very much like the sorts of objects we study in neuroscience, known as event-related potentials, basically gathering together fluctuations evoked in the brain inside by stuff on the outside, say visual stimuli, and then trying to look for systematic patterns. So this is actually an example from the literature from recording of a monkey exposed to visual stimuli, and these are the same data from this synthetic soup, just organized in a way to show the similarity. So lots of interesting issues here. Perhaps the most interesting one, though, is asking what's causing what here, because I've just talked about a mapping that is there because of the Markov blanket without really intimating that anything is causing anything, and of course nothing is really causing. If there is any causality, it is certainly circular. And I'm just making the point with this slide that what we're seeing here is a form of generalized synchrony that arises in a conditional sense via the existence of the Markov blanket. Is everybody familiar with generalized synchrony? Does everybody know this? This is the phenomena noted by Christian Huygens, that you suspend two clocks from the same beam, and after a while they will come to swing in synchrony and in harmony. So it is inevitable that any loosely coupled dynamical system will at some point find a synchronization manifold where they attain synchrony. And that's exactly what's going on here. There's just, because of this non-equilibrium steady state, there's a generalized synchrony between the inside and the outside, where from the point of view of our Markov blanket, we can imagine, so this is actually a drawing of two clocks, penduli, suspended from the same beam by Huygens, and we can associate one clock with the internal states, the other clock with the external states, and the beam basically becomes the blanket states that vicariously couple them. So what we're seeing here is just an instance of generalized synchrony, but with a special interpretation that arises because of this Markov blanket that I've cast in terms of this information geometry pertaining to beliefs about something. I just finished the technical part of this talk and then check how much time I've got left just by coming back to that functional that I have replaced the probability of the blanket states conditioned upon the model, the surprisal function. It rests upon associating the internal states with the parameters of a belief about external states. And this is a device that has been around for decades, if not centuries, and certainly in the past few decades underwrites approximate Bayesian inference and variational inference. So the idea here is, instead of trying to maximize the evidence or the marginal likelihood of some sensory data inherent in the sensory part of the blanket states in relation to the internal states, one tries to optimize a bound upon the surprisal or the integrated likelihood. And that bound is described here with this inequality here. So here is the surprisal of my blanket states, or we can think of this as, if you like, sensory data. And all we're doing by construction is specifying this bound in terms of the surprisal itself and the KL divergence, which is just the difference between the true posterior and the approximate posterior, as referred to in variational Bayes, denoted by Q, which is this belief distribution over external states parameterized by internal states, so that when the two are the same, this disappears and the free energy becomes the surprise or the negative log probability of some particular blanket states given a model of how those states were caused. Lots of rearrangements of this. I've just written a couple here just to motivate the use of the word, the term free energy. We can rearrange this into an entropy and an energy. From the point of view of a statistician, this is a very useful rearrangement of this expression here in terms of inaccuracy or accuracy and complexity, showing that, well, I should just say where the complexity is essentially the difference between posterior and prior beliefs, and the accuracy is the expected log likelihood of some data given posterior beliefs or under some posterior beliefs about how those data were caused, namely the external states. So essentially, evidence or surprisal is essentially accuracy minus complexity. So that is the construction from the point of view of a variational treatment of self-organization. We can cast this in terms of a variational principle of least action, which this simply says that given the existence of a variational density encoded by internal states, the most likely path of autonomous states of any given particle, given some sensory states, can be expressed as a gradient flow on this free energy functional. That's the summary. So the existence of a Markov blanket necessarily implies a partition of states into their internal states, the blanket states, namely the sensory and active states, and external or hidden states that are hidden behind the Markov blanket. And because active states change, but are not changed by external states, they're going to appear to minimize the entropy of internal states and the Markov blanket, and this means that action will look as if it is maintaining the structural and functional integrity of the Markov blanket. And people have talked about this in biology in terms of self-assembly, autopoiesis. At the same time, internal states will appear to infer the hidden causes of sensory states by maximizing Bayesian model evidence and influence those causes through action. And in the cognitive neurosciences, that's referred to as predictive processing or active inference. So it's inference with this action coupling back to the environment. I forgot about this. This is one of our students had a baby a few months ago, and his wife bought the baby a blanket, and that blanket has Markov. That's Markov on it. So that's an actual Markov blanket. You can buy them in America, and Franz kindly sent me a photograph of little Kira underneath her Markov blanket, making her inferences about the world. That's the technical story. I'm going to ask the organisers how much time I've got left, if any, to see if we want to quickly go through the neurobiologist version of the story. So how much time? Oh, lots of time, but presumably you'd like to have more questions than... I'm going to rush through this bit. Right, okay. I'll rush through this because I find the questions are usually more interesting than the presentation. I'm just basically going to say the same thing now, but using language that one would use if talking to neuroscientists and psychologists. We're going to be talking about predictive coding and neural networks. This whole notion of internal states looking as if they are holding beliefs about the causes of sensations, the sensory states, namely external states, is often interpreted in philosophy and neuroscience in terms of the brain as a constructive statistical inference organ, a machine that's there trying to generate explanations or hypotheses or beliefs about what caused its sensations. And this is beautifully illustrated by this still life artist in the 1500s, who was famed for doing paintings of vegetables that, when viewed from a different perspective, give you a very different impression as to how that was caused. So if you're now seeing a face there that you didn't see before, the key point is that you made that face, that comes from the inside out. It's not out there, it's an explanation that you brought to the table to best explain this particular pattern of sensory impressions. And indeed, the notion of sensory impressions is something which was beautifully articulated by Helmholtz in his attempt to understand perception. Here, objects are always imagined as being present in the field of vision, as would have to be there in order to produce the same impression on the nervous mechanism. So this view of perception turns around the 20th century view that sensory information impresses itself on the brain, and there's a cascade of higher order filters that somehow extract the information and enable you to recognize. We're completely, in the 21st century now, turning that around and saying, no, our perception really starts from the inside and works outside, and provides potential explanations or predictions of what we would see if this was the cause of our sensations, and then we actually use the sensory evidence to confirm or disconfirm what we thought was actually causing those percepts. And this idea is very closely related to Richard Gregory's notion of perception as hypothesis testing. Ideas that have been used to great effect by people like Peter Down and Geoffrey Hinton, by borrowing from Bayesian theory and using the formalism of Richard Feynman, the pathological formulation of variational free energy, to produce things like the Helmholtz machine and sort of simple variants like variational autoencoders in deep learning. All of these predicated on exactly the same legacy or heritage of ideas in terms of inference and constructing models that generate predictions. So let's come to this notion again of impressions on the Markov blanket, these sensory impressions that are registered by our sensory states. How might that be implemented in the brain? Well, we know because we've written down the gradient flow for internal states, so I've just expressed that now in terms of a gradient flow with the solenoidal part denoted by Q on the variational free energy as opposed to the actual surprisal itself. And underneath it, I've just rearranged it in a form which engineers will immediately or might immediately recognize as a Kalman-Bucy filter. So in this form, the solenoidal part becomes the prediction. Basically, if I have some beliefs about some external states that of some plant or some system that I'm trying to infer or track, then I know what their most likely next state will be, or the flow of those states will be, given my beliefs or expectations, mu, about the external states. And then the update term is basically using a prediction error to correct my beliefs based upon what I actually sense. And that's going to be weighted by a precision of those prediction errors here. So what's a prediction error? The prediction error is basically the gradient of that free energy here. More simply, let's imagine I had these sensory impressions here, and I had an expectation that they were caused by a howling dog. And if I had a generative model that could generate from this expectation what I would see or sense, if this were true, I can use the actual sensory input and the predicted sensory input generated by the generative model, subtract them, and form a prediction error. So this is predictive coding. So all that complicated, all that solution of the Fokker-Planck equation and the dual aspect information geometry can all be boiled down to basically a gradient flow and prediction error, where the prediction error is the gradient of variational free energy, rendering the objective function a sum squared prediction error, as we all know in having sort of schoolboy statistics. So all we're saying is that systems will look as if they're trying to minimize their prediction error. It's not necessarily saying that they will hold beliefs about the veridical state of the outside world causing their sensations. That's not the point. The point is they will look as if they're trying to minimize the prediction errors based upon their explanation for the patterns of sensations registered by the sensory states. So that provides a very simple picture of action and perception in the brain, because there are two ways you can minimize prediction error. You can either change your brain so that you make your predictions more like what you're sensing, but there's another way of doing this. You can change the senses, the sensations that you're sampling, to make them more like what you're predicting, and that's the active part, that's the action part. So we have this very simple picture where the brain's trying to change to accommodate and make predictions that are closer to its sensations, whilst at the same time actively sampling the world to make the sensations close to the predictions. So the action tries to realize the prophecies of the perception of the internal states. And we'll come back to that if we have time in a second. Just formally, in terms of what these gradient flows would look like from the point of view of neural circuits and neurophysiology, we have to consider the form of those generative models that generate the predictions from the expectations. They are highly nonlinear, they're dynamic, and they're deep in the sense that they have a hierarchical structure. And if one just looks at the message passing implied by that gradient flow and that variational free energy under these deep generative models, then one gets a scheme which looks remarkably similar to the way in which we think the brain actually does pass its messages around. And that essentially involves flows of descending predictions, generating from the inside out predictions of sensory input and all other intermediate expectations in a deep or hierarchical generative model, that is complemented by an ascending flow of prediction errors that perform or contribute to the update part of this sort of extended Kalman-Bucy-like filtering perspective on brain dynamics that has become known as predictive coding. So I'm going to finish now just with an illustration of that. I'm going to go through this very, very quickly, just so I can show you a couple of movies. What I normally do here is just go through an example of functional anatomy in the visual system, making the point that we have prediction errors at multiple levels. The first level here, a prediction error about visual information coming from the eye that is subtracted from, the other way around. The visual information here minus the top-down predictions performs a prediction error here. The predictions pass back up, but these now are these predictions at the first visual level are themselves being predicted by higher order parts of the generative model. So you have these second order prediction errors that are then sent forward to revise more abstract beliefs and so on and so forth. And I just wanted this graphic is really to make the point that the action is important in the sense that there's another sort of information in the sensory states. That's basically the state of my muscles, where I'm currently looking. Now, of course, I can make inferences infer where I am looking, but there's a simpler way to resolve those prediction errors about where I'm looking. I can simply contract my muscles so that they send the predicted signals. Now, that's important for two reasons. First of all, it's simply a description of a classical motor reflex arc that causes us to move, so that feels right in terms of understanding the biology of moving creatures. And also, it now makes these top-down predictions commands. They're basically set points, like a thermostat. If I can make a prediction that my reflexes will come true, then my predictions become the prophecies that are actually realized by my motor plant. And that's under the active inference view, basically how we think the brain works. This was a demonstration of slow pursuit where the agent believes that there's a visual object out there that has to be tracked, and there's an invisible leading object that's pulling both the object and the eye. And if one writes down that generative model, applies the gradient flow, then you can reproduce almost exactly the sort of visual tracking movement that human beings show, and also deficits that you see in things like schizophrenia when you adjust that precision or that gain of the or sensitivity to the prediction errors. But the point being made here is that the generative model can be very different from what's actually going on out there. Here it actually has a belief that there's this there's an invisible, if you like, tractor that's pulling both the target and the eye, that allows the eye to preempt movement, follow through occlusions of the target, and do all that good stuff that we are able to look at empirically in human eye tracking. The final example was an example where we use the same device, but now we're not pulling the eye around, we're now pulling the hand around, and using that to simulate a very elemental form of handwriting based upon a generative model that has a heteroclinic cycle, so a dynamic generative model of movement that we're then mapping to particular locations in some pointing space. And then the top-down predictions essentially become commands. The descending proprioceptive predictions basically tell the reflexes where to move the hand, whilst the corollary discharge, as it's sometimes known, provides the visual predictions, which means that the brain or the internal states can gather information from multiple modalities and do this fusion to have this coherent belief about what's going on out there. But crucially, it was actually authoring what was going on out there. There are no, if you like, attracting points pulling the hand around out there. This is all being authored on the basis of the generative model of the internal states that is being fulfilled by writing into this universe that particular structure and those particular beliefs, thereby minimizing surprisal or minimizing free energy, and everything's working nicely with its pullback attractor in play. But it's all come from the generative model, not the universe. So to conclude, here's this phrase: objects are always imagined as being present in the field of vision, as would have to be there in order to produce the same impression on the nervous mechanism. What we'd like to do, or what the last few examples we're really trying to speak to, would be to take this one step further, that once you get this sort of recurrent coupling between internal and external states implicit in a Markov blanket, then it's not just a question of representing stuff on the inside. You're actually authoring the dynamics of stuff that's going on the outside, and you're very actively then inferring your lived world. And that's it. So all that remains really is for me to thank the people whose ideas I've been talking about, and of course thank you for your attention. Thank you very much indeed.